Domain theory. It is a common observation that whenever a magnet is broken into two, we always end up with another magnet. So when we take a single magnet, for example a bar magnet, and we break it into two equal portions, we end up with a pair of magnets with both the north and south poles. The process of breaking a magnet can be continued as long as there is a magnet to be broken. However, it would mean therefore that because magnets are made up of particles, i.e. a magnet is matter, then the process can be continued until the smallest indivisible part of the magnet is reached. This indivisible part, or the smallest unit of a magnet, will still have the north pole and the south pole. The smallest unit, or that small magnet, is known as a micro magnet, or simply dipole. So it means therefore that a magnet is made up of small units that we call dipoles. The dipole has the head, which represents the north pole, and the tail, or the lower end, that represents the south pole. If we take a magnetic material such as iron, then the iron as a material would be made up of the small dipoles. The dipoles are arranged in regular manner within small subdivisions known as domains. So within the domains we have dipoles. For an unmagnetized material, the arrangement within particular domain is regular. If we take maybe domain A and domain B and domain C, then there is a regular arrangement of dipoles within these domains. If we take domain A, let us compare the arrangement with domain C and B. We note that the dipoles are arranged in a manner such that they form concentric loops. That is, the north poles of the domains in partition A are arranged in such a way that they face the south poles of the dipoles in domain B, and that the domains in domain B faces the north poles of the dipoles in domain B faces the south poles of dipoles in domain C. So, according to domain theory, domains are microscopic groups of atoms with the same magnetic orientation. When placed in a strong external magnetic field, domains aligned with the external field grow in size. Other domains turn towards the external field, and if it happens that all the dipoles in these domains have been allied to a particular direction, then we get a magnet. So if we compare diagram 1 and diagram 2, then diagram 1 represents an unmagnetized magnetic material, while diagram 2 represents a magnetized material. That is to say, diagram 2 is a magnet. So if we compare the two, then we note that in one, the dipoles are arranged in a concentric manner, while in two, all the dipoles in all the domains face the same direction. And in such a case, the material is said to be magnetized.